Hi, everyone. Welcome back to another Talk Math with your friends. Today, our speaker is Brendan Sullivan. He is an assistant professor at Emmanuel College, and today he will be speaking to us about ChaserRunner games. So please join me in welcoming Brendan.
Hey everybody, thanks for coming. I'm going to talk about the ChaserRunner game and product graphs and how we can use products to create some interesting structures on which to play the game, and also how those two products play a starring role in a particular algorithm that we can use to calculate some features of the game. So yeah, I'm at Emmanuel College. We're in Boston, just a stone's throw from Fenway Park, and I'm coming to you from Cambridge, just across the Charles. And here's my contact info down here. I just want to point out that on Twitter, I had to get rid of the N because I ran out of characters. So I'm Professor Brenda over there, but on Gmail, I got the N in there. So just a subtle difference. Oops. And we'll come back to at least this particular graph. If you're wondering what these things are on the cover, we'll see that one a lot today. So rather than wait till the end, I thought I'd start with a couple of thank yous. First of all, to everybody organizing the Talk Math with Your Friends seminar. I submitted an abstract a few months ago and said I'd be available later in the semester. And then TJ got back to me and I said, well, how about a little bit later? And you all were gracious to accommodate that. So I appreciate it. Just kind of math Twitter folks in general. I'm sure a lot of you found out about this on there. So I appreciate that community that has really helped me stay in touch with the math world while kind of living at home for a long time. And pretty much all of the work that you'll see here has come out of summer research projects with these 5 students over the last 5 or 6 years. So I wanted to highlight Nico and Michaela and Sarai and Bo and Osa, who have all contributed meaningful parts to this project. And in particular, I owe a big debt of gratitude to Nico, who really started this project. I have a doctorate in math, but not a PhD. And so I started teaching at Emmanuel and did not have any kind of research program going at all. And Nico came to me and said, I'd like to do some math research over the summer. What does that entail? And I said, let's figure that out together. And a lot of what you are going to see today came out of that. So Emmanuel has been very supportive of that. And in particular, one of my friends, Deepak, who does some research in this field, was the guy who kind of gave us this idea to start with. And I've been talking with my friend Sean over the last couple of months to bring myself back up to speed on a lot of this stuff. I haven't been great about keeping up with research over the pandemic, and so he's been super helpful in getting myself back up to speed. So I appreciate that. And everybody here or watching this later on YouTube, thanks for your interest. So I have a bunch of goals, and I'm going to break these down in over the next couple slides as well. But just to remind everybody, hopefully, when I say graph today, here's what I mean. A little structure like this that has some vertices, the dots, and some edges, some connections between them. And for today, all of our graphs are going to be finite in the sense that there are not an infinite number of vertices. They're all connected in the sense that we don't see something like this stray vertex over here that doesn't touch anything else. We're not going to be dealing with situations like that. And we're going to be dealing with graphs that are undirected in the sense that you could travel back and forth along an edge. There's no inherent one-way roads or anything like that. So overall, I'm going to give you an introduction to Pursuit-evasion games and a couple of variations. We'll get a kind of quick history of the field and what's known and what's open. Another thing I'll do is try to suggest some new terminology. I'll talk about that in a minute. And overall, I hope a big theme you get out of this is that I'm posing a lot of open problems and calling for collaborators. So feel free to contact me after this and during the chat throughout the whole time. I'll try to keep up and see some questions, but feel free to call stuff out. That's important.
So we have a question already.
Yeah,
which is
the loops and multi-edges. So we're not going to actually draw any of the loops, but one of the rules of the game is that players can pass their turn. So effectively there is a loop at every vertex, but we're not actually going to think of them as included in the graph. And same for multi-edges. That doesn't, at least the variants I'm looking at, that doesn't change the game in any way. So we'll just assume there's one connection. Great. So I'm going to recommend a couple of resources for just learning about kind of what's out there in this field. In particular, there's a book by Anthony Bonado and Nowakowski called The Game of Cops and Robbers on Graphs. It comes from the AMS student library. It's a great survey. Highly recommend it. My book is falling apart from having paged through it so often. And I'll recommend another thing, and in no way am I claiming that they are equal in scope or quality or anything like that, but on the second thing there, I'm recommending a paper that came out of this summer research with a couple of students, Nico that I mentioned, and Kayla, where we looked at a particular variant called the lazy cops game. And so that's in the College Math Journal, and I think it's a readable introduction to that variation, not for a technical audience. Some other resources, I've put together a folder. So essentially any paper that I talk about or mention today, there's a PDF copy of it in this Google Drive folder that I just put in the chat. And also in that folder is a document with a list of open problems and conjectures that I'll mention today. So if you're trying to remember later, what was that thing that puzzle that I could work on, check that list, it's probably in there. And after today's presentation, all of my written annotations on these slides, I'll make that a PDF and put it right up there in that folder as well for everybody to have. Two of the things that are mentioned in there are these videos from a PBS YouTube channel, a show they had called Infinite Series. I believe it is now defunct, so I don't know if anybody will answer that Gmail address down at the bottom left there, so don't contact them. But they did have a show for a while. And they had 2 episodes about the cops and robber game. So if you're looking for some more information about it, check those out. They're short videos. All right, so one thing that I'd like to do today is to suggest, and really this is kind of a test for myself, just to see if I can go through this whole presentation saying chaser and runner instead of cops and robbers, just because that's kind of what I'm used to. And I don't think anything is lost by changing the terminology to chaser and runner instead. And in fact, I think it avoids a lot of unnecessary baggage that I just frankly don't need involved when I'm thinking about and working on this stuff. And so that original formulation as cop and robber come from a paper from the 1980s by Richard Nowakowski, who you see over here in green, and commensurate puzzler, Peter Winkler, who you see over here in blue. And they just said a graph is given and 2 players, a cop and a robber, play the following game. And then that was kind of it. Since then, it's been called cops and robbers, and all sorts of whimsical terminology and variations have come out of that. But it doesn't necessarily have to be that way. So I'm just going to propose that I use the chaser and runner, because it at least preserves the C and the R notation that I've grown accustomed to. And like I said, I don't think we lose anything in terms of understanding anything about the game.
Excellent. I think Elizabeth had another idea as well.
Yeah, go ahead.
She just put in the chat, Coyote and Roadrunner also preserves the letters and is very silly.
That's
Cats and rats, yeah.
I've heard cat and mouse too, but Coyote Roadrunner is the first one I've heard that also keeps the CR. So that's interesting.
Great, thank you.
We're going to come back and play on these 2 graphs in a minute. But something interesting I just noticed yesterday while rereading this really short paper of theirs, just a couple of pages, is that this kind of introduced this game to the world and first characterized graphs that require only 1 chaser to win. And in the entirety of that paper, these are the only 2 figures. And I thought that was just kind of interesting, and an interesting embodiment of how math writing tends to be kind of dry and technical and lacking figures. And I think this is a particular area where pictures are good. So I'm going to try to use a lot of pictures today. So another thing I'll mention is that I believe the chaser runner idea is a little more faithful to the origins of the game that goes back even further than that paper. That was kind of one of the first mathematical results about it. But I just learned somewhat recently about this guy named Ernest Dudeny, who seems to me in my quick reading to be kind of like a Martin Gardner figure in England. And so he published a lot of puzzle books back in the early 1900s. He has a whole book that kind of spoofs the Canterbury Tales in puzzle form. So what you see here in this figure is an example of a puzzle from that book that's essentially a find an Euler circuit in this graph puzzle, phrased in terms of a very old Englishy tale like the Canterbury Tales. And so he published a book in 1917, I think it was, called Amusements in Mathematics. And that's really where I think this game came from. So this picture you see over here, I took from a post on Anthony Bonado, the author of that AMS book I mentioned, from his blog. And it proposes essentially this game, except the one difference is that this picture has specified where the two players start. And one aspect of the game we're gonna learn in a second is that we will allow the players to choose where to start. But for this one, there's a British general at B and some kind of enemy at E. And then the goal of the Britisher is to chase down the running enemy. And that really is this game that we're gonna investigate. And I just wanted to note that, yeah, this was published in 1917. And if you think about what was going on with Britain at the time, as we should suppose from the analogy of real life, the British general must infallibly win. I thought that was some interesting language around that. So it wasn't really a puzzle so much as just like, hey, we know the Brits should win. So anyway, I just hope this kind of justifies me trying out this chaser runner terminology, just kind of to see how it goes. So another thing I mentioned is that I'm going to be sharing a lot of open problems and conjectures throughout here. And in particular, I wanted to highlight an upcoming event happening later this summer in the first week of August. There's a 2-day conference called GraphScan, or Graph Searching in Canada, about Pursuit-evasion games, but also other related topics in graph theory and applications. And the first day before that, the Wednesday, August 4th, is specifically a kind of summer school for students, for undergraduates who are interested in learning more about participating in research in this area. And so you can see one of the topics is Pursuit-evasion games. There's also some others, metric dimension of graphs, zero forcing, and graph searching. So if you're curious to learn about this field and related stuff, this is something you can check out. There you go. Okay, so enough talking about what I'm going to talk about. Let me just start doing it. Here are the rules of the game and a couple of variants mentioned within the rules. So the chaser team, they are allowed to initialize and start themselves anywhere they want on the graph. They could start on the same vertex if they want, and at any time we'll allow multiple chasers to occupy the same vertex. There's no problem with that. Then knowing where the chasers have started, the runner initializes somewhere on the graph. Throughout the game, there's perfect information, so everyone knows where everybody else is. And then the turns alternate. So the chaser squad gets to move their pieces, the runner sees what they do and gets to move their piece, and they go back and forth. So by move, I mean along an edge. A legal move is along one of the edges of whatever graph we have specified to play on. And there are two main variants that I'm going to be talking about today. The ordinary game is where all of the chasers on their squad are allowed to make a move at the same time. So when it's the chaser's turn, each piece can do its own move independently, although we assume there's one player controlling all the pieces, so they optimize their strategy. In the lazy variant, the other one I'm going to talk about, we'll restrict it to be more like the game of chess, where you have a whole squadron of pieces at your disposal, but you're only allowed to move one at a time. So maybe lazy isn't quite the best way to characterize that, but it's kind of what has stuck. And so that's the variation where there's only one chaser moving at a time. In both of those variations, we're going to allow for passing. So this is that point I made earlier about effectively there's a loop at every vertex, but we're not really going to draw them. And I see Joss's question in the chat. In fact, yeah, historically where the lazy variant came out, there was a paper by Offner and Ojakian where they were looking at certain fractions, certain proportions of the chasers being allowed to move at a time, like maybe half the team or 100% of the team. And the most extreme version where only one is allowed to move at a time, that has since gained the lazy nomenclature. But yeah, that's the one paper I can think of where it's looked at different proportions of the chaser team being allowed to move at once. So really, I understand there's probably going to be a lot of questions about like, well, what if I change that rule? And what if we did this differently? Or, you know, what if the runner moves randomly? What if the runner knows where the chasers are, but the chasers don't know where the runner is? And really, any of those questions are good, and you've probably just invented your own variant of the game that you can go and explore and write a paper about. And some of them may have been invented and investigated already, but maybe not. And so that's one theme I want to get out there, which is you take these rules and modify them a little bit, you've probably got something new to explore that nobody's looked at before. So what are the winning conditions? If there exists a winning strategy whereby one of the chasers lands on top of the runner, obviously the chasers win, they have captured the runner. And we have this weird winning condition for the runner whereby they essentially don't ever lose, and that's the way that they win. If there exists a strategy where they can just move around the graph forever and never get caught, that's what we're going to call winning for the runner. So over here, I have one of those figures from the Winkler and Nowakowski paper. Let's try playing on this graph as an example. So I'm going to use R red runner for the runner piece and blue for the chasers. So let's start with just one and see what happens. Let's say I choose the chaser to start on this vertex right here, let's say. Where would the runner probably choose to start? Well, if they're being smart about it, they're not going to start right next to the chaser. They're probably going to go somewhere else. And so probably as far away as possible, let's say something like that. And then let's hold that one off for later. On the chaser's first move, they can go like this. And now we can see that the runner's not caught, but they're about to be. They're essentially in what you might call a corner or a trap or something like that, where if they pass their turn and they stay still, they're going to get caught on the next go. Or if they take the one move that's available to them, they're going to get caught on the next go. So they are doomed to lose. And if you think about it, this didn't depend on the chaser starting at that particular place, and it didn't depend really on where the runner started either. One chaser is going to be able to win on this graph no matter what the runner tries to do. And that's what I mean by there exists a winning strategy. So if you don't remember, the the other figure of that paper added a couple of edges. I think it was like this. Let's see how that changes things. Let's try the same thing. Let's start the chaser here. And we saw that the runner was probably going to start there, but now that's a bad move because of the addition of that edge. So let's instead have them start somewhere else, like right there. What might we try? Anybody have any suggestions for a good chaser move? Attack somehow, right? So basically try to maybe narrow the distance, move along a path between the two of them. So what if I tried something like this? This at least makes a threat. This is forcing the runner to actually move and not pass. And it looks like they can get out by moving up to that vertex up there. And so the runner is going to say, all right, I'll go closer to you. I'll go to where you just were. And in the old graph, that was going to be it. They're going to get caught here. But now we've opened up that extra edge. And so the runner says, I'm over here now. And if you think about it, this is just going to keep happening. The chaser is going to try to box them in over here, and the runner is going to say, well, I'm going to go back over there. And they can do that dance back and forth forever. There's actually nothing that the chaser can do that's going to corner the runner. And as Kim put in the chat, a good way to see this as no matter where the runner is, and no matter where the chaser is threatening them from, there must exist a vertex they can move to that will maintain a distance of 2 between the two of them, and therefore they will never get caught. Awesome. Here's another example of a graph that I'd like us to try. This one has 40 vertices, so it might take a little longer to play on here, but I'm curious. Where would you think, well, first of all, can anybody see yet what's going to happen with one chaser here? If I only allow one chaser on this graph, can anybody see what might happen before I have to play this out too much?
Stephen hypothesizes the runner wins. Yeah, probably a big loop of some type.
Yeah, if you notice, this graph is like full of little cycles, little loops. And so essentially, if they start here, the runner can just wait. The runner can just effectively pass their turn until they really have to go. And the only time that's going to happen is if the chaser gets to this point and then they decide to make an attack. And that might involve going like this. But as you can see, that has now opened up that column right before them. And so the runner is going to go over there. And if the chaser says, well, I'm going to attack you over there instead, then they're just going to go right back to where they were. And there they're going to do that dance back and forth forever, just like we saw in the other example. So let's try 2 chasers instead. Let's see what happens with that. Just somewhat arbitrarily, I'm going to say, let's start them here. And let's have the runner start somewhere at the top. Any suggestions for like a overall kind of strategy for what the chasers might be thinking of doing here?
Maybe try to trap the runner on the top or the bottom.
Seeing that they're already up on the top row, I can see that being a good idea. Maybe they want to move up. And along the way, maybe they just want to think carefully about whether the runner could somehow pass through down towards the bottom. They want to squeeze them up to the top row. So maybe the runner would pass here. And then, is this equivalent to a chess game with kings? Yeah, if you ever find yourself in a chess game where 2 kings are battling one other one, I'm not sure why that would happen in a real chess game, but that's effectively what this is, yes. And so the move, I think, is for the 2 chasers to kind of narrow in while preventing the runner from getting out in any particular direction. And so maybe here they would try to get out this way. And so then we begin this chase towards the corner, essentially. And what's going to happen is, just like in the previous iteration, we're going to have this situation where one of the chasers can kind of box the runner in the corner. And whereas before, with only one of them, that led to that stalemate dance where they went back and forth. With 2 of them at their disposal now, they can keep one of them there and then just kind of send the second one in to capture. And that will end it. Now I put more here as a question to preview a later idea, which is if I had 3 chasers on here, that might make them win maybe faster. It might help them cut down on the number of moves it takes, but it's not gonna somehow make them lose instead. But that's something that we might talk about a little bit later. So here are some ideas that came up while we were just talking about this, and I'll put some terminology to some of them. Deciding who wins is based on existence of some kind of optimal strategy and not how people would actually play the game and trying to figure out. So I'm not necessarily recommending this as like a fun, game night activity necessarily. This is more about like identifying optimal strategic play. And we're going to call the chaser number of that graph we just saw 2, because one chaser was not enough to ensure victory, but 2 guaranteed it. So that cutoff point. And to prove it, we had to do 2 things. We had to look at it from the chaser side and say, effectively, given 2 of them, here's how you can definitely win no matter what the runner tries to do. And that was the kind of box him in the corner strategy. But then on the other side, we had to show that the runner could get away from 1 fewer chaser. So we had to look at it from the runner's perspective and say, they will evade only 1 chaser. And so any proof about a chaser number is going to have to involve those 2 parts of the proof, exhibiting a strategy from both sides. With that particular number of chasers, so for that graph 2, but in general, for any graph, if you have the optimal number of chasers, they will win no matter where they start. And so there's an idea of maybe if we had been more judicious about how we played, we could have started the chasers like in the middle kind of to cut out more of the graph. And maybe we could have trimmed down the number of moves it would take. What I'm talking about there is this notion of a capture time. And we didn't even really try to find it over there. I was really just saying 2 are going to win. But if you wanted to, we could investigate what's the optimal number of moves. If the chasers are simultaneously trying to make the game go quickly and win as soon as possible, whereas the runner, knowing they're bound to lose, if they're trying to make the game last as long as possible, how many moves is it actually going to take? That's what we're going to call the capture time. And in general, that's a lot harder to find. But also, I hope you realize that there wasn't anything special about this being an 8x5 grid, really. If this was a wider or taller grid, 2 chasers are still going to be enough. It just might take a lot longer to win. And so in general, the big questions we're interested in are about classes of graphs. And I kind of like playing on specific examples to get a handle on it. But the kind of big results in the field are about, you know, oh, for all grids of any size, what can we say about them? Those kinds of questions. I see in the chat here, yeah, there is a variation called tipsy chasers and runners where there are coin flips involved and making moves randomly. Really, any variant you can imagine, it might have already been looked at already. All right, so I mentioned the capture time there. Turns out that's something we can compute. And so it turns out this is known for the ordinary game. For both, by the way, I didn't mention that. We had both of the pieces moving at the same time. We'll come back to the lazy variation later. But allowing both of the chasers to move at the same time, it's known from this paper in discrete math from 2010 that the capture time, the optimal number of moves it will take, is this quantity right there. So we had a 5x8 grid. 5 plus 8 is 13 over 2 is 6.5. Round it down to 6, subtract 1, you get 5. Turns out 5 moves is the optimum, the best you can achieve. And what you see over here is the output from this code that my students and I put together based on an algorithm described in the paper. So I defined the graph by taking 2 paths of length 8 and 5 and putting them together somehow. I said test 2 chasers, and it said, yeah, they win, and the capture time is 5. And by the way, here are the 4 initial positions you could start on that achieve that time. And if you start at any other position, you will still win, but it will take more than 5 moves. That's what the output of this code means. So one thing that's kind of interesting I've noticed that I'd like to explore more is that there's often a lot of symmetry to these things. So 12 and 27 are these 2. And 16 and 23 are these 2. And 17 and 22 are these 2. And 18 and 21 are these 2. And it's saying that you got to start on one of those colored pairs to achieve the optimal capture time. And there's some nice, pretty symmetry to that. I think there's something deeper going on there. And I don't know if a whole lot is known about those things. So here's an open area that is worth investigating.
That feels like the cake cutting problem because the runner chooses after. You sort of have to, those have to be the ones where all the choices are exactly the same.
Yeah. I think that there's another feature going on here, which is going to come up later when I talk about the graph products. But just to preview that, you can almost see how this graph is kind of two paths put together. And notice that all of those pairs, both of them involve kind of starting in the middle of each of the two paths. And so if you think about how one chaser would be playing on a path and trying to make the game as short as possible, they can definitely win by starting at one end of the path and traveling across because they're bound to bump into the runner at some point. But if they want to cut down the number of moves, they're going to start in the middle and just move outwards to whichever side the runner started on. And that's kind of happening in both directions on this larger grid graph. So there's something happening there, something profound as well. So some other related open questions are for higher dimensional grids. If you have a 3-dimensional thing or higher, I don't think the exact capture time is known for those. So that's something you could explore. And I'm not aware of, other than some stuff my students have done, I'm not aware of any progress on the capture time for this grid with the lazy variation where only one chaser can move at a time. I don't know of any publications about that, but that's a nice, relatively simple problem to get started investigating.
And Josh has a question in the chat. This is a min-max kind of thing where it's a minimum of a maximum. So is the initial placement of the chasers always unique for optimal catching time?
I don't think so. In particular, we saw here that there are 4 different positions that the chasers could start on that achieve it. And some I'll show you later have a great number of them. So no, it's often very far from unique, but it depends, of course, on the graph itself. And
then the same question for the runner. Where they go, I mean, obviously if they pick right next to the chasers, they lose. Yeah. So it has to depend. That one I haven't looked at a whole lot. It's just that the code outputs for us kind of the chaser perspective of the strategy. So I haven't spent a whole lot of time looking into how the runner prolongs the game. That's a good question. I need to look into that myself. Great, thanks. So here's another instance of this theme. Let's tweak something. And so this time, rather than one of the rules, let's change the graph to allow for diagonal moves in that grid. How does that change how the game is going to play out? So let's start with 1 again, just to see how it goes. Seeing that we might want to start in the middle, I'm going to do that again. And the runner's probably going to start somewhere far away. Now, what's a good idea for the chaser to do here? Seems like they got to head upwards at some point, and they also get a head off to the right at some point. So maybe their first move is going to go like this. So they're a little bit closer to being on kind of the diagonal where the runner is. I don't know, maybe the runner tries to get out and starts to go like this. Well, the chaser says, I'm going to try to squeeze you towards the side of the graph. And the runner's realizing they're running out of room, because at this point, now they're going to get caught by the diagonal move. And in particular, what we don't run into is that stalemate situation where the runner's stuck in the corner and the chaser is holding them there. Now they're actually threatening that move in that process. And so, in fact, 1 chaser is going to be enough on this graph. Let me try to I think I can prove that 0 is not enough. Yes, right. So for free, we now know that this is 1. And also, there's no sense of laziness anymore when there's only 1 anyway, also. So we don't have to worry about that variant. But let me try to preview an idea that's going to come up pretty soon by saying, try to think about try to see how what I'm doing is I'm playing on a path and a path. And I'm almost enacting the strategy in both directions at the same time. And so right now, if I think about how the runner is kind of like here on this factor, on this path, and the runner is here on this path, and meanwhile, the chaser is like here and here, what's the optimal strategy on this path over here? It's to move up towards the runner. And what's the optimal strategy down here? it's to move over towards the runner. And so the good strategy to do is both of those moves at the same time, because that's allowed. And then no matter what the runner tries to do, let's say they go like this, then now we've effectively caught the runner on that path, the horizontal version. And no matter from now on where the runner tries to go, the chaser can always mimic that move left to right while simultaneously making progress in the up-down direction. So at this point, they would probably just go like this. And then no matter where the runner goes at this point, they're going to get caught on the next go. Can I come back to the planar question? That's something I'll mention in a couple minutes. So by the way, here's the code run on that graph. I just want to highlight a couple of things. First of all, it says one will win, and it's a very quick calculation, about a 3,000th of a second. But I also wanted to highlight that this code can do things like testing more chasers than you need and wondering whether that cuts down on the capture time at all. So just for the heck of it, I tried, well, I know I only need one, but what happens if I have two? And we can determine that that's only going to take 2 moves. So there's another kind of big open question on graphs, which is if you allow for more chasers than you need, how does that shorten the capture time? That's a big open question. All right, so here's a bunch of things that are known about this game. And the first couple things come from this particular paper by Aigner and Fromm from the early 80s. That's in that folder I linked to. First thing is they made an inductive construction to show that chaser numbers can get arbitrarily large. So there exists graphs that require 100, 1,000,000, whatever chasers. And surprisingly, they proved that a planar graph will never need more than 3. And this still kind of boggles my mind, but it did lead to a whole bunch of interesting kind of like topological genus-related results. And I'm just going to highlight a particular survey by Bonado and Mohar about topological directions in cops and rubbers. If you're curious about how topology plays a role in this field, check out that survey. I found myself somewhat interested in extremal questions of like, what's the smallest thing that satisfies a certain property? So one example is that the force cycle, which we saw was, the lattice grid had these little cycles out the wazoo. These cycles are the smallest example of a graph that really needs 2 chasers. And this graph that you see up here, the Peterson graph, that was proven to be the smallest one that requires 3 chasers. And interestingly, the 3 of them can win by starting on what's called a dominating set, where no matter where the runner starts on their first move, they will always be 1 step away from one of the chasers, as long as they start on those 3. So this is an example where they win and the capture time is 1. But if you only have 2 chasers, they're always going to lose. So there's something interesting going on there. And that one of those graphs that was on the cover of the presentation, that is a graph that my students and I found, which is the analogous result for the lazy variant. We found that 9 vertex graph, which is the smallest example that requires 3 chasers when we're only allowed to move 1 at a time. There's some stuff known about capture times, but in my reading of the field, not as much is known as there is about chaser numbers kind of in general. So there's been a lot of work on graphs that only need 1 chaser and determining what the capture time is on those. The Offner and Ojakian team have done a lot with that, but that's kind of a big open area. Yeah, let me talk about this one. What if I allow for this grid to be wrapped around a cylinder? Or in other words, I imagine this grid with the spaces and the diagonals, and I'm allowing it to go around. Or another way to think about that is kind of a Super Mario thing, where if I have a piece and it's on this
square, I'm allowed to teleport and end up on the other side of the screen this way. Oops, I forgot to.
There's been a lot of Pac-Man chat in the.
Yes. I gotta copy this stuff. There we go. So let's say the pieces start like this. I'm going to say that let's look at it in a similar way where I have something going around this way and something going up and down this way. And the pieces are going to enact their strategies on the two factors kind of separately and play them at the same time. So right now, if I'm thinking of a cycle, a loop like this, and I have the two chasers like this, and the runner kind of effectively in between them, the chasers, their goal is to move in to try to capture them that way. But at the same time, it seems like they want to move up to get closer to the top row where the runner is. So they're going to move kind of in and up like this. And now they've kind of captured the vertical column of the runner. And so no matter where they try to hide out next, they're just going to maintain that while simultaneously getting closer by moving up. And so they're going to eventually get caught towards the top by like that. And so here's where I finally reveal something that I've already kind of partly revealed, which is all of the, or some of these graphs that I've shown you are created from other graphs. And this is meant to motivate the products that I'm going to talk about now. So I want you to think about those lattice grids, whether or not they have the diagonals in there, and think about them as a path times a path. And the inclusion of the diagonals or not is just a different product of whether we allow those to be included or not. But other than that, they're essentially a path times a path. They're the two factors. And so those two products are called the Cartesian product and the strong product. And the individual notations are meant to evoke what exactly they do. So if I had an edge times another edge under the Cartesian product, it will produce exactly that shape that you see. The formal definition being any kind of graph product, G times H, the vertex set of the product graph is ordered pairs, where the first coordinate is a vertex from the G factor and the second coordinate is a vertex from the H factor. And the only difference between these products is what kinds of edges get included. And so in the Cartesian product, edges are of the form where one of the coordinates is fixed, but the other one is allowed to change along an edge in the corresponding factor. So that's kind of like, you know, going from here to here is like fixing the second coordinate, but changing your first coordinate. And something like that is the other way around. For the strong product, it includes the very same stuff, but it also adds the diagonal moves in the sense that you can change both your coordinates at the same time. And so that's what that lattice grid with the diagonals was. It is like going from here to here. That's allowed in that strong product because it's like moving along an edge in one of the factors and moving along an edge in the other factor. And therefore that's allowed to be a single edge in the product. And I want to highlight this language of changing only one at a time versus changing any number of them at a time, because that should ring some bells like the ordinary variation of the game where all the chasers can move, and the lazy version of the game where only one chaser can move at a time. There is a relationship there. So let me do this. I'm going to skip over some of the stuff here and talk about this particular graph just because it was on the cover and I need to say what it is and how it is a product. So first of all, let's practice thinking about this by saying, what is a complete graph times a complete graph? So by K3, I mean a complete graph, so 3 vertices and all pairs of edges are there. So it's effectively a little 3-cycle or a triangle. So if I did K3 strong K3, then I'll think of that as 3 copies of that graph. And I will include edges of the form changing one or both of the coordinates at a time. So for example, from here to here is an edge because that's kind of fixing my first coordinate and allowing me to change my second coordinate. which is allowed because it's a complete graph for that second factor. So all the possible edges are there. But also, this is going to be an edge because I'm allowed to change both. And so without drawing a whole bunch of them, this is going to actually be a complete graph on 9 vertices, and that's not going to be very fun to play on because no matter where the runner starts, he's going to get caught on the first move. So we're actually just not going to bother with that one. But instead, the Cartesian product is much more interesting. And we get this thing over here. And so let me just, instead of ask you, let me just tell you how this plays out. If you have 2 chasers, they can win very quickly by starting on the opposite corners. The runner must therefore start in the middle. And on their first turn, one of them will capture the row and one of them will capture the column. And then where's the runner going to go? They have no possible moves, and so they will get caught. But let me back that up and say, what if I'm only allowed to move one at a time? What if I enact the lazy variation? All of a sudden, when I try to capture the row, that vacates the top row and the runner's going to get out. And if I try to capture the column, that vacates a column and the runner's going to get out. And so that completely changes the game in the sense that 2 aren't going to be enough anymore. And it turns out we need 3, and they will just dominate the graph by covering, let's say, 1 per row. And no matter where the runner starts, they're going to get caught on the first turn. So when I mentioned earlier, my students and I found the smallest graph that requires 3 lazy chasers. This is that graph. And it is the 3x3 rooks graph because the edges represent the possible moves of a rook in chess where they can go side to side or up and down. And so another way of viewing this is the smallest example of a graph where the chaser number and the lazy chaser number are actually different because the regular one is 2 and the lazy one is 3.
Is it easy to see that this is the smallest?
Not really. So we took that code that I have and I ran it on all graphs up to 9 vertices to calculate their lazy chaser numbers. That took about a month to go over about 300,000 graphs. And it did say, yeah, but of course we then had to go back and prove it. And it's really just a very detailed like cases argument. So it is probably a slicker way of doing it, but that was the best we found. So I'm going to skip over a couple other things too and jump ahead to the main idea of the algorithm, which is using those products to represent the states of the game. So let's simplify things a lot and say, I'm going to play on this 5 cycle with 2 chasers. So we know exactly what's going to happen, but I want to try to get you to visualize how we might represent what's happening in the game by keeping track of where the chasers are. So like, for example, this vertex right here in a product graph, 0, 3, I could think of that as corresponding to having a chaser on vertex 0 and the other chaser on vertex 3. And in the, let's just for now, for sake of argument, say the lazy game, what's a legal move that I could do from here? I could possibly move the guy on 3 over to 2. And so there deserves to be an edge from 0, 3 to 0, 2, because that's a legal move in the game space. Having a chaser at 0, 3 and a chaser at 0, 2, it's a legal move to get from one to the other. But for example, I couldn't simultaneously move both of them. Oops. I couldn't move both of them, so there is no edge from that to 2, 4. Like that is not a legal edge. And as it turns out, what this is really doing is if you're playing on a graph G with K chasers, then you can do the exponential, essentially the K-fold product of G with itself, K times, to represent all the possible positions, all the game states of all the chasers. Because essentially each vertex in this big giant product graph G to the K is a K tuple where each coordinate represents the location of one of the chasers. And then the only difference between the ordinary and the lazy variations of the game are that, going back to what I said on the definition slide for the products,
The strong product allows you to change all your coordinates at the same time. That's like changing all the positions of all the chasers at the same time. So if you're playing the ordinary game, use the strong product to do that exponent. Whereas if you're using the lazy variation, you're only allowed to change one coordinate at a time. So use the Cartesian product. So I have this code, and basically there's a little if that says, do you want to do lazy or ordinary? And if you do one, you do the strong product, and if you do the other, you do the Cartesian product. That's it. That's the only difference between the two variations of the game in terms of how the algorithm runs. So rather than trying to diagram that all out for you in the last couple of minutes, I'll just kind of skip ahead to some fancy stuff and say that it's cool, but very slow. And so let me illustrate that with an example that I ran today. So here's that 8x5 lattice grid again, this just 40 vertices, not a whole lot. And we know that 2 chasers is enough, but just for the heck of it, I tested 2 lazy chasers and it found the capture time of 9, and that took about 30 seconds to run. And to test 3 chasers on the same graph, that took about 10 minutes to run. And so the idea is, I think it's on the order of like n to the 2k plus 2 or 3, something like that, where n is the number of vertices in the graph and k is the number of chasers. So essentially adding another chaser multiplies the runtime by how many vertices there are on the graph. And so I did manage to run this for 4 chasers, and that took about 2 hours. And so this is, I think, a really great resource for calculating stuff, but it's just kind of too slow to handle any like large and super interesting graphs. So I'm looking for ways to speed this up, to improve it. And so I'm kind of calling out for anybody who has some coding expertise and wants to contribute to this, or if you have any suggestions or insights, I could really use the help. I'll end by just saying, here are some of the big questions that I'm kind of interested in investigating. What is it about a graph that makes the chaser number and the lazy chaser number different? I believe that those rooks structures that I mentioned are the smallest examples that make them different. But I'm wondering in general, what is it about a graph that makes that happen? I've noticed a lot of examples where for a certain number of chasers to win, they effectively have to dominate the graph. What is it about a graph that's making that happen versus something that requires a bunch of moves? I'd be curious to know about that. As far as proofs go, I'd say in general, it's much easier to come up with chaser strategies than runner strategies. Why in the world is that? I'm curious. And as we increase the number of chasers beyond the minimum number required, what's the playoff there with the capture time? That's a big kind of open area of investigation that I don't know a whole lot about. And really, I am interested in using this code that we have to build a kind of database of, calculating known information about graphs. Because one thing I didn't mention is that the output of this code is not just the, true, here's where you start, here's the capture time, but also stores essentially a dictionary of all the optimal strategies of both sides and how they should play on the graph. And so every time I run this calculation, I then lose all that info. And I'm wondering if I could somehow start to build a database of known stuff about small graphs to try to explore some patterns. So happy to answer any questions you all have at this point.
Is unmute and join me in thanking Brendan. So many questions. Anyone have one they want to ask?
So I guess I want to chime in if it's okay. So Brendan, really liked the talk, very nice. I guess one thing I want to come back to, apart from the research you presented, is the name of the game, right? Because I think that's a very provocative idea. It's something that's come up a fair bit recently. So of course, this game has been traditionally called Cops and Robbers, which we all know has a lot of baggage with it, especially these days. But Chaser and Runner is a very good alternative to it. Of course, the issue is that there's this body of literature that exists now for 40, even actually going longer than that, 40 plus years. And changing it is quite like a heroic effort. And there's a lot of resistance within, maybe not surprisingly to this crowd, like you can imagine within the math community. So even when I started using gender neutral pronouns for like the chaser and runner, cop and robber, there was pushback from referees, right? They wanted he and she. And they say, oh, well, it comes from combinatorial game theory with Richard and Louise guy and that kind of thing. But there are a lot of other things going on behind that. So, I don't know, I guess I'm just sort of opening up to discussion, and I'd like to hear your perspective, Brendan. I mean, just changing the name, like changing the name of Matroid, which, like, no offense, probably not the best name, right? Like that would be really difficult to do because it's just sort of an embedded thing. And when I talk to like all of the researchers that I know in this field, like it doesn't resonate at all, changing the name. So I just would like to throw that out there for discussion.
That's partly what I was trying to do here too, just to throw it out there and say, hey, if I could get through this presentation, I think I only slipped up a couple of times accidentally, but just to demonstrate, like, look, I can do it. I think everybody was following along pretty well. Like I understand the pushback, but I don't know what I would say to them, but I just hope that this demonstrates that it's possible to just not use cop and robber and still be okay. That's all. But yeah, I'm curious what others think too.
I think there's a lot of alternative terminology out there that just happened historically. Like somebody called it one thing, somebody called it some other thing. So I'm not, introducing alternative terminology is not a breaking fact. You can nod at in your footnote. Some authors call this cops and robbers and leave it at that, just so you can have the literature out there. I study T2 spaces and Hausdorff spaces, and they're the same thing, but some people call them one, some people call them the other.
I guess the challenge here is that like all of the literature refers to cops and robbers, like every single paper and book and everything. So you write a paper with chaser and robber, or chaser, there I go, chaser and runner, right? Mm-hmm. You're gonna be the singleton. And it takes maybe someone to start doing that, but like, who that person or people going to be. And so this book that I'm writing, I mean, I decided to stick with cops and robbers, but this discussion has made me think a lot about, I think not so much a footnote, but sort of just maybe adding a paragraph or so, sort of acknowledging that name has challenges for a lot of people and there are alternate terms that people have considered.
I think even doing that would be a pretty big important step. Yeah.
Well, I have lots of thoughts, but we're at our hour, so I'm gonna let us have our pause here. Let's thank Brendan one more time. A lovely talk, especially modeling sort of like the opening up a research question. I believe we are planning to take a bit of a break. We'll update you via Twitter and some other things. Beyond that, I'm hopeful that we'll still see each other a little bit soon, but we'll update you more with that soon. Yeah, great. So if you need to go, this is at the end, but maybe somebody can hang out for a couple of minutes.
I'm happy to stick around for more questions. I'm here.
Great, thank you.
Brendan, I have to run. Stephen already logged. Oh,